In this video, we'll begin our discussion of section 14.2. This will be talking about iterated or a double integral, which looks pretty intimidating on the surface, but actually is just backward integration using respect to one variable or the other, or we're going to lead into triple integrals in the next coming section. So the volume of a surface over a region, so it's not area under a curve, but rather volume under a surface, is noted like this. So we have V equals our double integral over some region R, and then this is going to be the trickiest part for us, is that dA. What is the dA? Well, if it's an area, right, and it's going to represent a volume over all, but it's just like when we do dx captures the whole x, it gives us a whole like dimension. dA is going to give us an area dimension. So if it is an area dimension, we won't talk about where this comes from, but dA, and I have it written there, but I'll write it here, is dx dy, right? It's an area component, x by y. We also, because multiplication is commutative, right, we can do it in any order, this is dy dx. I can do either one. This is going to be the key to these problems, because if they are the same thing, what we're going to be looking for is which one is easier. That's really what it's going to come down to in these problems, is figuring out of these two, which one should we do for an easier integration. Sometimes it won't matter, sometimes it will. Sometimes it's impossible one way and possible the other. All right, so with that, these two things here are equal. So notice the only things that are changing are, okay, so let's color code here. That goes, let me make these a little smaller. So notice that A and B go with that dx. So notice that this dx here, A and B got moved to the outside like the dx. Now, if I do dy, notice that dy here goes with C and D. When dy was on the outside for this first point, so was C and D. They go together, so if you flip them, you have to flip your bounds as well. The bounds go with each variable. That's going to make sense as we set these up on why that is extremely important. It's going to come down to the way we define them. Okay, so let's get a couple examples in this video down. We have the double integral of x plus y squared over dA. We know dA is dy dx over the region R, and they define R for us. Where we are headed, do not, unless, and we're going to do a few of these problems like that, where we're not going to draw a picture, but most of the time we're going to draw a picture. So I'm going to give myself a decent, I don't need very many numbers here, but let's graph our region. So this says all x's that are between 0 and 1. And then this says all y's that are between -1 and 2. So we are talking about the region between -1 and to 1, 0 to 1 here, all the way up from -1 to 2. So we get this region right in here. So verify that that is, sorry for my terrible box there, but we are trying to find the volume. So this is our x and y. We should label that, right? This was x, this was y, right? And we have that picture. There is a surface Z coming out at us, and we're going to find the volume of the surface above that rectangular region. It's not like Calc 1 where we can just say, hey, integrate from 2 to 5. We don't have this like area anymore that's underneath. We have a volume. Well, I can't just say in 3 dimensions go from 2 to 5, because that doesn't actually give us a direction. We have to have the two-dimensional shape telling us what volume do you want from the three-dimensional picture. All right, so we set it up now. I always set this up first, going volume equals, and I just don't write anything down yet. Write down my x plus y squared, and then I sit and decide, do I want to do x or y first? I think x looks easier, so I'm going to do it first. So we got dx dy. So my x is first, so I get my bounds from my x's. You should look in the picture and in the description up here, the R region. This says from 0 to 1. The picture also verifies that. So 0 to 1 goes with the dx. So notice here, that this dx, the highlighter I should have made big again. Hold on one sec. I know this is annoying. dx goes with 0 and 1. So the dy on the outside has to go with its bounds. Well, y was -1 to 2. Right. So we have that double integral. How we evaluate these is we evaluate the inside first and then the outside. So we'll go -1. I'm going to rewrite this for a moment just so you can capture this to make sure you understand what we're doing. Then we'll take that answer and do it with dy. So we'll have the answer on the inside, so we'll do that first. All right, that is integrating with respect to x. So we get x squared over 2, normal integration. And then this is going to be weird. This is the part that you're probably going to forget. It's just like the partial derivatives when we have something of this manner, right? And I take the derivative with respect to x, we just get y squared. So if I'm starting with y squared and I go backwards, I get an xy squared. Now, since it's a definite integral, meaning we have bounds, we don't have to worry about a plus c. So that's just smack dab. I don't even know how to use that expression. I won't even try. It's right there in the middle of that integral, right? I just have to evaluate the integral. So I plug the 1 in. You can see that. And remember, and actually, I'm going to do something here. It's going to be really annoying that I'm going to make you go back and redo this. But we should be doing this. And trust me, I know it's annoying, but it's going to help a whole lot. X is between 0 and 1. Y is between -1 and 2. The reason I forgot is I'm fighting against my own habit of doing it one way for a long time. So what is happening here is we have x to 0, x to 1. And the reason we do this, and I'll explain when we get up here, is that when we get to this point, right, I'm going to go ahead and write just those. We can leave those because at this point it won't matter. Actually, no, we should do it. Fighting my laziness here. Y equals 2, y equals -1. And then the reason we do this is because when I plug it in here and I'm about to evaluate it, this is the whole reason, this is where all my students mess up that don't do this, is they will plug 0 and 1 into the wrong variable. If I write my x's and y's the whole time, it's clear what that goes into. They go into my x's. So I get 1 over 2 plus y squared minus, and then it's just going to be 0. dy, and then I'm dropping my my bounds because now they're only y's. Right, I hope that was okay. We're just plugging in 1 and we plugged in 0. So now we integrate this, right? So this is 1/2 y plus y cubed over 3. It's just a normal derivative, and then now we run these bounds from 1 to 2. So we get plugging in a 2, we get 1 plus 8 over 3 minus, plugging in -1, we get -1/2 minus 1/3. You could plug all that in your calculator if you need to, or do it by hand, whatever you prefer, but that ends up being a 9/2. So the volume under the surface of that pink space there is 9 over 2. If I go up, it's a positive volume, so some of the surface may go below, some of it may go above. I think all these will go above if we look at our z. This is our z, by the way. So this is the surface, right? The integral, that's the whole point. The integral over that surface. So that's my surface there. I can tell that if I plug in the x's and y's inside that region there, it's always going to give me a positive number. So the surface is sticking out at us from the screen. And we know the volume under that surface in this pink rectangle there is 9 over 2. All right, let's try another one. So the surface, so z equals 2xy. That's my surface. And then, like I said, I always draw my region because I don't want to lose sight of what I'm doing. And then as well, the sections towards the end of Calc 3 get really gross, and we need to be able to do this. Okay, so the first thing I'm going to graph is I know y is between 0 and that function. Okay, I know that one has an intercept at 1. I also know that when x is 0, y is 1. The graph looks something like that. You could plug that in if you need help. I also know that x equals 1/2. It's right there. All right, so, and it's saying between 0 and 1/2. So the region that we are going to find the volume over will be right here. So the surface either goes up or comes down, but up or below, the z is sticking out at us and going into the screen, and we want to find how much volume is in that region under that surface. All right, so I always first set this up, write down my surface, and then I got to pick a direction. This looks arbitrary, so I'm just going to do, this is a big point. My y, the bounds are 0 and 1 minus x. That tells me that dy has to come first, because when I plug my bounds in, I'm going to get an x. I want to get a number, right? So I would not want this to be here, because my final answer would have an x in it. All right, so we should write y equals here. Like I said, I'm fighting a bad habit of myself. And then x equals 0 to x equals 1/2. That's my dx. All right, so we have our integral. We just handle it one at a time. So let's do the integral on the inside first. X equals 0, x equals 1/2. And we're with y, so we're going to get x, y squared, right? Go up by 1, divide by the new one. All right. Hopefully that's okay. If not, think about taking the derivative of what's in the brackets there, and that'll take you back to what's above. Now, I have to plug in my bounds. So x equals 0 to x equals 1/2. And then we're going to plug that in for, and this is why that's important. For a moment, I was like, oh, what does it go into? Well, it's y. Okay, so y goes into that. And then 0 is going to get me 0. Hope you can see that. So we get x times 1 minus x dx. That's just plugging in square root of 1 minus x. That gets squared. That's why it's in parentheses now. And then plugging in 0 for y is just going to give me a 0 term. All right, I'm going to rewrite this. This is x. There are only x's now, so I'm not worried about writing all those bounds down. And this is x minus x squared. I like seeing that better. It's easier for me to handle. Okay, so we can take our derivative. X squared over 2 minus x cubed over 3. We're running that from 0 to 1/2. All right, plugging all that in, we get 1 over 8 minus 1 over 24. That's plugging in 1/2 minus 0. And that's going to end up being a positive 1/12 once you do all your arithmetic there. As we go on, I will do less and less of this part because I trust that you can do it. We're just going to work on the integration. All right, so we'll stop this video here.